American theoretical physicist Michio Kaku is the author of several books about physics and has worked on research in quantum mechanics. He has a remarkable approach to explaining things that make hard ideas like quantum physics and string theory seem understandable to us simple humans. How I make ends meet is string theory, that is my day job. And you see, string theory is a multiverse hypothesis. So, individuals express, above all else, what is string theory? String theory just says that all the particles we find in nature, the electron, the proton, the quarks, what have you, are something else, with vibrations on a melodic string, on a little, tiny, little string, you know. Robert Oppenheimer, the maker of the atomic bomb, was so disappointed in the 1950s with the multitude of subatomic particles being made in our particle smashers that he declared one day that the Nobel Prize in Physics ought to go to the physicist who doesn't find another particle that year. Well, today we imagine that only melodic notes exist on these little vibrating strings. So, what is physics? Physics is the harmonies you can compose on vibrating strings. What is science? It is the songs you can play on these strings. What is the universe? The universe is an orchestra of strings. This is the strange universe of quantum physics as we investigate the bizarre and interesting peculiarities of the subatomic reality, where particles act in ways that challenge our regular understanding of reality. We will misrepresent these ideas, and hopefully, you will forgive us for doing so since there is nothing harder to comprehend in science than quantum physics. As Richard Feynman once said, if you think you understand quantum mechanics, you don't understand quantum mechanics. At the core of the quantum world lies the atom, the building blocks of matter that were once thought to be indivisible. Yet, as physicists delved deeper into the atomic world, they discovered that particles don't act like the regular objects we experience. In the quantum world, particles exist in a haze of probability. They can be in two places at once and have a mysterious connection that Einstein called spooky action at a distance. To make things even stranger, particles seem to be affected by the observer, as if they know they are being watched. But that's not all. String theory takes us even deeper into the puzzling scene of subatomic particles. According to this theory, particles are not tiny dots but rather small strings that vibrate at different frequencies, creating the spectrum of particles that make up our universe. It is fascinating to think that millennia ago, ancient Greek philosophers like Democritus attempted to understand the atomic world using reason and logic. You know, Pythagoras was an opponent of democracy. Democracies debated atoms ages ago, and Pythagoras said, no, music is the language of the universe. So, he looked at a lyre string and said, look at the vibrations, each vibration corresponds to a musical note. The universe is music. The universe is made by vibrating strings. Each vibration corresponds to a note. He went to a blacksmith, where there were long bars of metal, and they were striking these bars of metal. He realized that the longer the metal, the lower the note. There's a connection between the length of the object, its strength, and the note. And then he looked at a lyre string and said, the longer the lyre string, the lower the note. Then he said, this is the universe. But what explains the variety? What paradigm is rich enough to explain the variety of the whole universe? Atoms, but what makes atoms different? Then he said, it's music. But they never went anywhere with that idea, of course, because atomic theory wasn't developed for another 2,000 years. But finally, with atomic theory, we now have subatomic particles. Yet, why do we have so many subatomic particles? They're just melodic notes on a tiny, tiny, vibrating string. String theory has also led to some intriguing ideas, such as the possibility of a multiverse, where our universe is just one of many. While this idea is purely theoretical, it shows that the quest to understand the subatomic world is far from over. Some of the greatest minds in science have tried to understand quantum theory. One of the most notable was Albert Einstein, who believed in a hidden reality that we can't directly observe. He rejected the idea of entanglement, but as experiments continued to prove the validity of quantum theory, Einstein's views became increasingly marginalized. When I was 8, something happened to me too. It was in all the papers that a great scientist had just died, and they put a picture of his desk on the front page. That's it, just a simple picture of the front page of the papers, of his desk. That desk had a book on it, which was open. The caption said more or less, "This is the unfinished manuscript from the greatest scientist of our time." So, I said to myself, well, why can't he finish it? What's so hard that you can't finish it if you're a great scientist? It's a homework problem, right? Why can't he solve it? To me, this was a murder mystery. This was greater than any adventure story. I wanted to know why the greatest scientist of our time couldn't finish something. And then, over the years, I figured out the man had a name, Albert Einstein. And that book was the theory of everything. It was unfinished. Well, today, I can read that book. I can see all the dead ends and false starts that he made, and I began to realize that he got lost because he didn't have a physical picture to guide him. On the first attempt, he talked about clocks, lightning bolts, and meter sticks, and that gave us special relativity, which gave us the atomic bomb. The second great picture was gravity, with balls moving on curved surfaces, and that gave us the Big Bang, the creation of the universe, and black holes. On the third attempt, he missed it. He had no picture at all to guide him. Well, today, we think that picture is string theory. String theory also suggests the existence of extra dimensions beyond the three we are familiar with, a mind-bending concept that raises the possibility of multiple universes, each with its own set of physical laws. These parallel universes, also known as the multiverse, are a popular theme in science fiction, but they are also a serious area of study for scientists. The idea is that every time there is a decision to be made, the universe splits off into two or more possible outcomes, each occurring within its own separate universe. String theory could also help explain the mystery of dark matter, the elusive substance that makes up about 27% of the universe, yet we can't directly observe it. One explanation is that dark matter is made up of particles known as WIMPs, weakly interacting massive particles, which could be produced by the vibrations of strings. While there is still so much we don't know about string theory, it has opened up new avenues of research and shown us that the universe is far more complex and wondrous than we ever imagined. However, string theory must be more precise. The string hypothesis has also been heavily criticized by the scientific community. One of the main criticisms is that it is difficult to test or falsify. The theory requires the existence of extra dimensions beyond the three we are familiar with, but these dimensions are too small to be observed directly. Another criticism is that the theory has yet to make any predictions that can be verified through experiments. Despite decades of research and numerous mathematical advancements, string theory has not produced any definitive results that can be tested in the lab. Some scientists argue that the theory is too complex and convoluted, requiring the existence of multiple universes and exotic particles that have yet to be observed. While string theory has the potential to revolutionize our understanding of the universe, it is important to approach it with a critical eye and to continue exploring alternative explanations for the mysteries of the subatomic world. I would say that any field of research, when it's new, is bound to attract attention, and the media sources are going to cover it, and students will flock to it, sure. But as a field matures, it sheds those qualities because it's no longer as novel as it was when it was first introduced 30 or 40 years ago. But you need to judge it by a different standard. You need to judge it by whether it is making progress on fundamental questions and expanding our understanding of the subject. By that measure, string theory is scoring very high. At the same time, you also need to judge whether it connects to experimentation, too, and in that measure, we're still challenged. So, I would say many string theorists, myself included, are very level-headed about the theory. It has made tremendous progress.